Okay, welcome to our second lecture, online lecture. I hope you are enjoying it. Page table, today we're going to talk about page table implementation issues and how to improve the memory access time by using a structure called a TLB or an associative memory. And we will also do a little bit computation about how to quantify the access time when we are using paging and TLB tables. Okay, so when we're talking about the paging, we said every process needs to have a page table. Depending on the configuration of the system, this page table could be big or small. So one question is where to store that page, right? When we were talking about the paging, we said that page table is actually stored in the main memory as well. But actually, if it is small, maybe you could actually store the page table in the register, so that will be really fast for memory accesses, because we can convert the logical addresses to physical addresses within the CPU. But since the registers are limited, we can only deal with small size page tables. In general, page tables tend to be large, so in that case we would like to use main memory to store that page table entries. However, in that case, when we are accessing data or instructions, every time before accessing that actual instruction or the data, we need to access the page table. From the page table, we need to know what's the frame number for the instructions we are interested in. Then we can go and get that instruction or the data from the main memory. So we will end up going to memory 2 times, right? So to speed up that process, well, we will see a data structure or a mechanism called the dedicated lookup tables can be used. Okay, so where do we store the page table? As we mentioned, it's stored in the main memory, and every process has a page table, and the location of that page table is transparent to the user programs, but the operating system knows about this page table by maintaining its base address and then the length, etc., in the process control block. So when your process is scheduled to run, the CPU or kernel knows where your page table is. Okay, so as I mentioned, the issue here is when we maintain the page table in the main memory, access time is an issue. So to speed up the access time, we will be using a dedicated lookup tables, or sometimes called the associative memory, or sometimes called the translation look-aside buffer. That's what TLB means. And in the next slide, we will say a few more words about these data structures and mechanisms, basically. Okay, so basically what is an associative memory? So basically in the traditional memory, what we do, we have an address, right? We go to that location, and from this location we get the content into the CPU and use it, right? So the associative memory goes the other way around. So in the associative memory, what we have is we do not want to access these elements by the index number. What we would like to do is we would like to access things by content. So if I am looking for a certain information, we will assume that different types of informations are stored here. In our case, the page numbers, different page numbers are stored here. And when I'm, let's say, page number 5 is stored here, 7 stored here, 3 stored here, 4 stored here, right? They could be in any order as well. So let's say at some point, if I need to access page 7, okay, if I need to access page 7, in this case, in the page table case, I need to use the 7 as an index and go, and from that I can get the frame number for page 7, and then I can go to that frame, right? But in the associative memory, we will get the 7, but we cannot use 7 as an index on this data structure. Instead, what we have, for each page, we will just maintain that page information in the memory, plus what is the frame number. Let's say this is frame 1, frame 2, frame 3, and frame 4, let's say. And now when the 7 is given this data structure in parallel, that's how it is designed in the hardware, it searches that keyword here in the memory. When it finds a hit, okay, it gets you that output saying that F7 is mapped to F2. Okay, so this way, this table can be maintained in the cache or can be maintained even somewhere closer to the CPU, so we don't need to go to the actual physical memory every time to get the frame. But the problem with this data structure is it is small. You cannot put all the pages here, right? So you can only put a limited number of page number and the corresponding frame numbers into that table. That's how you can make it faster and closer to the CPU. So then in that case, what it makes sense to use the most frequently used pages here. So this way, when there's a reference for this page, we don't need to go to the physical memory and look at the page table. We can just simply look at that page number within that data structure, which is faster, closer to the CPU, and we can easily get the frame number for that page, and then we can just simply compute the physical address as we did before. Okay, so that's the key idea. And now let's look at it one more time within the big picture we looked at before. So the CPU generates an address. We can divide that into two parts, P bits and D bits for the page number and the offset part. And the traditional method of paging, we just simply use that information, P bits, as an index on the page table, which is also in the physical memory somewhere here. Just logically we are showing it here. And then from that table we get corresponding frame number, and then we copy the frame number and the offset bits together, and then we create what's known as a physical address. Okay, so the problem with this idea is we need one memory access to get that information from the page table. Then we need one access to actually now access the instructions or the data we are trying to access. Okay, so we have two memory accesses, and this is expensive. So what we are planning to do is now we are introducing a new associative memory or TLB table, which is you can think of this as something closer to the CPU like registers or cache, but it's not in the main memory. It is a much faster memory, but it works differently. How it works in this case, since it is small, we cannot afford to put all page numbers here and the corresponding frames here. We will only put the page numbers that are used frequently here as a content in the memory. So let's say page number 1, page number 7, page number 3, whatever they are, and the corresponding frame numbers, let's say frame 2, frame 7, frame 0, whatever they are, right? So now this time, when you introduce that hardware or the memory within that architecture, basically what happens when the P bit comes in, we first search these P bits in parallel within the table. And if it matches with one of them, then right away, let's say if we are searching for page 7, it will match with this. So right away, we will get a hit and copy that F bit here. And then we can just simply combine with D bits, and then we can access the physical memory. So, okay, here now what happens is accessing this memory takes time, but it is definitely much faster than accessing the physical memory. So let's say this takes epsilon amount of time, which is less than one memory access. Once you resolve the physical address, then you have to access the physical memory one more time. So total it will be epsilon plus 1 seconds or nanoseconds to access the data. In this case, it takes 2 nanoseconds to access the data. Okay, so that's the key idea behind the TLB table and how it works. Okay, what happens if, let's say if I'm looking for page 10, and when we search it, page 10, let's say, is not here. Then, of course, this will fail, so you cannot resolve this address, but all the pages are in the page table anyway, so we have to go and look at the usual thing. So we will use this page 10 as an index. We will come to look at the table. From the table, we will find the frame number, and then we will resolve the address. So now this case, this epsilon plus 1 happens if there's a hit, right? If the page number we are looking for, if hit happens. Else, the total time that we are spending to access the memory, clearly we will spend epsilon time, but it fails, right? Then we will spend 1 time for accessing the page table, and then runtime to get the actual data. So that will be the total 2 plus epsilon amount of time. But the good thing here is, now later on we will see, the average of these two numbers, this plus this, depends on how often this step happens and how often that step happens, basically. Okay, now let's quantify that excess time. And as I mentioned, let's assume that associative lookup time is epsilon time unit, and the memory cycle time accessing the main memory takes m time units. Okay, so the epsilon is much smaller than m. And we would like to also introduce another idea called the hit ratio. That hit ratio tells us out of, let's say, 100 page reference, how many of them are found in the associative memory, and then the remaining parts are not found in the associative memory, right? So it's basically the percentage of the times that a page number is found in the associative memory, basically. And that ratio is called alpha, basically. Okay, so if I say the hit ratio is 0.7, what does that mean is out of 100 memory references, 70 of them will be in the memory and 30 of them will not be in the memory. So with probability 0.7, something is in the memory, and with probability 0.3, something is not in the associative memory. Okay, so now when we take this into account together, then the effective access time, so the average access time basically, can be computed like this, right, in a weighted manner. So it will be something like this. So with that probability, the page that we are looking for is in the associative memory. So if it is in the associative memory, as I mentioned in the previous slides, it takes epsilon amount of time to look at the table, and then since it is there, we spend m amount of time to get the actual data or the instruction. And with 1 minus alpha probability, what happens is we look at the associative memory, but the page is not there. Then we spend 1 memory access time for accessing the page table and looking at the page table. Then we spend another m time units to access the actual data. So that's where that 2m comes from. I think we already explained this in the previous slide. Here I'm just taking their weighted averages, right? 1 minus alpha times 2m plus epsilon, and alpha times m plus epsilon, basically. Okay, let's just make a quick numeric example here. So let's say, assume that the associative memory lookup time is 20 nanoseconds and the memory cycle time is 100 nanoseconds. And here's the assumption. We're assuming that the hit ratio is 80%, means that 0.8 probability. So alpha is 0.8. With that probability, the pages that we are looking for will be in the associative memory. With these numbers, what will be the effective access time, right? So just pause the video and try to compute it by yourself, then we will check your answer. Okay, I hope you find out like this. So basically, with that probability, 0.8%, 80% of the time, we access the associative memory, 20 nanoseconds, and the data or the page that we are looking for is there, and then we spend another 100 nanoseconds to go to the memory and get that instruction or the data, right? So that will be the total effective time for accessing existing page numbers in the associative memory. However, the other side is with 1 minus 0.8 probability, we will access the associative memory, but we will not find the data there. So then we have to go to the page table. So we will spend 100 nanoseconds, and then definitely it will be in the page table. So then from the page table, we will go to the actual physical address and get our instruction or data. So total we will spend 200 nanoseconds. So altogether it's going to be 220 nanoseconds when the page page we are looking for is not in the associative memory. So altogether, when you do the math here, we will figure out that effective access time is 140 nanoseconds. So to understand this number, you have to look at two extreme cases, right? In the old system, when everything is in the memory, when we are using the direct memory accesses, we were spending 100 nanoseconds to get everything, right? If we just simply use the paging as a regular system without any associative memory, then every memory access takes 2 cycles, one for the page table, one for the actual instruction. So it was 200 nanoseconds. Now 140 is a compromise between these two numbers. It is not as good as 100, but it is much better than 200 nanoseconds, and we are getting all the advantages of paging that we have been trying to get, right? Another exercise here you can do is if you increase the effective access time. So basically, if your program keeps using the same pages, then it means your hit ratio will increase. Or if you just increase the size of that associative memory a little bit, maybe you will maintain more pages in that table and hit ratio will increase. So if you increase the hit ratio, let's say to the 89%, and if you do the math with these numbers, you will see that the effective access time is going to be around 122 seconds, and it's almost same as the traditional system where you have to maintain addresses contiguously, and it's much better than just basic paging. So as you see, a simple data structure and a little bit hardware addition to the architecture gives us a significant better results, and we should take advantage of those things. And also, when you are writing programs, maybe you should think, how can I improve the success or the hit ratio of my program? I mean, we will give one example later on. Okay, so let's just stop here.